A sodium ion and a chloride ion are separated by 2.82 times 10 to the negative 10th meters. Find the electric force on each ion. So this problem looks a little bit familiar, but in this case we're looking for the electric force and not the electric field. And we're looking for the electric force on each ion, which means I choose my point of interest to be either here or here and find the electric field from the other charge, and then multiply it by Q in order to find the electric force on that charge. But they asked me a question here which is going to make the problem simpler. So they ask, how should the electric force on the sodium ion compare to the electric force on the chloride ion? By Newton's third law, these forces should be equal in magnitude. And opposite in direction. If they ask me a question like this beforehand, if I can answer the question, it might save me some work when I do the mathematical analysis. So the point of them asking the question is so that you only have to do one calculation in the mathematical analysis section, and then you can just say something like, by symmetry, the other force would be equal and opposite. We're also supposed to sketch the direction of the electric force on each charge. This ion is positive and this one is negative. Those are opposite charges, so they would be attracted to each other. Okay, so let's look at the force on the chloride ion. So I want to find the field at this point from the sodium. So we're going to find the electric field from the sodium, and then we'll use that to find the force on the chloride ion. So this distance is 2.82 times 10 to the negative 10th meters, or since it's 2 blocks, we can call it 2a. And the sodium is a positive charge, so remember for the electric field we do K times Q. It's an ion, which has a charge of E, divided by R squared, that would be 2A squared, pointed in from the charge to the point of interest. That's pointing this way for the sodium, so that's in the I hat direction. If you wanted to find the field from the chloride with the point of interest being at the sodium, the sign would change because it's a negative ion, and R hat would change also because from the charge to the point of interest is that way, which means in both cases the field would end up being in the positive I hat direction. To find the force, this is the force on the chloride from the sodium. Oops. The force is equal to the charge times the electric field. This is the charge at the point of interest, and this is the electric field from all the other charges at the point of interest. So this charge is negative E, and we multiply it by K times E over 2A squared. That's pointed in the I hat direction. So we get negative KE squared over, let's call this 4A squared in the I hat direction, and then we can plug in some numbers. So this force is going in the negative I hat direction, and we said if we found the field at this point from the chloride ion, it would be pointing in the I hat direction, but then you multiply it by a positive charge, and the force is still going in the I hat direction. So the force on the sodium ion is going in the I hat direction, and the force on the chloride ion is going in the negative I hat direction, as we showed there. So now I just have to put in some numbers, and I have 9 times 10 to the 9th newtons times meter squared per coulomb squared. E is 1.602 times 10 to the negative 19th. You don't have to use as many significant figures as I did there. And this is 2.82 times 10 to the negative 10th meter squared, pointed in the I hat direction. And when you calculate that, you should get, rounding to two significant figures, 2.9 times 10 to the negative 9th newtons in the I hat direction. And then we'll just say by symmetry, the force on the sodium from the chloride is equal to negative 2.9 times 10 to the negative 9th newtons in the I hat direction. So we'll box this and this. That was a rather cumbersome way to label the force. Maybe a better way would be to call this charge 1 and this charge 2, and then this would be the force that 1 exerts on 2, and this would be the force that 2 exerts on 1. So that might be a better way to do it. Also, remember that they give you the answers in the back of your book, and you should really check that for homework, because if it's not correct, you might want to go back and fix it. So now we're in the electric force section, so if you turn to page 45 in the electric force, it showed us that the force on the chloride should be negative 2.9 times 10 to the negative 9th newtons in the I hat direction, which is, that's this one. That is what we said. Okay, and that's that. Except that I see now that I lost a sign here. So this was the force on the chloride. That should be pointing in the negative I hat direction, and I had my negative sign there, but I failed to carry it through, and this one would be positive. And then when we check the answer in the book, we see the force on the chloride, which is what I have here, is the negative one. So that looks better.